Now, if you happen to have a turbojet, or you're thinking of buying one, or if you watch our video series on this subject, we'll show you how to build one. You really might want to consider adding an afterburner. These little devices can add a substantial amount of thrust for relatively low weight, low cost, and ease of assembly. It's a pretty good thing. Now, not all jet engines are turbojet engines. There are pulse jet engines, pulse detonation engines, ramjet engines, and even the very first forays that were made into the construction of commercial scale turbojet engines were done a little bit before World War II, where they took powerful gasoline engines to drive the compressor stages that compressed the air before the fuel was added, and they produced the exhaust blast. And our very first videos on the jet series also used a hybrid type of design, where we took some powerful EDFs, or electric ducted fans, about 5 kilowatts each, placed them in series, and produced a modest level of compression before we added the fuel, heated the exhaust, and nearly doubled the output from the fans alone. It really worked. One of the problems, though, with any of these designs is the enormous amount of energy that's necessary to drive the compressor stages. Just to give you an idea of the magnitude of that power, if you look at the Allison 250 series of turboshaft engines, these are small turboshaft engines that have been around for decades and produce a rotary mechanical output being driven by the exhaust gases, by a turbine, and can range from about 350 to about 900 shaft horsepower. In those engines, the turbine stage actually sends only 1/3 of the amount of power that's extracted to the output shaft. Twice as much power as you take out is actually recirculated to drive the compressor stages, and that's a small engine. Another example is this turbocharger over here. This single stage compressor, just this little part of this turbocharger, at full power will consume about 250 horsepower from just this little thing. The power is enormous. And so that's why early on the military designers decided to take the hot, high-pressure, high-velocity exhaust from the jet engines, run a turbine, and send that power to the compressor stages. It was lighter and more powerful than the gasoline engines, and hence the birth of the modern turbojet engine. We decided to make the same sort of transition and got away from the hybrid design and started building jet engines based on the turbocharger to turbojet conversion. Now, this is actually a pretty popular project, and there's a lot of YouTube videos out there about it, because it's relatively easy to do. Because there are millions of these turbochargers built every year, all of the expensive engineering, the design, the precision machining of the compressor wheels, the turbines, the housings, the bearings, is spread out over millions of examples. And so all you really have to do to construct the turbojet is to build the combustion chamber. It's not trivial, but it's a heck of a lot easier than the other components, and if you watch our videos on the subject, we show you how to do it. Now, what makes building an afterburner possible is that all turbojet engines pass substantially more air through them than they actually need to burn the fuel. The reason for that is that if you take that ideal mixture, that golden ratio or stoichiometric ratio of fuel and air, and you burn the fuel so that you use up all the oxygen, you use up all the fuel, and at the end of the reaction there's nothing left behind, you produce a flame temperature that is so high that you would almost instantly melt anything downstream of the flame. So what the designers do in a turbojet is they take the compressed air that comes in from the compressor. They send some of it into the combustion chamber to burn the fuel. And then as those very hot exhaust gases are moving down toward the turbine, they allow additional air to dilute that hot flame, more air than was actually needed to burn the fuel, to bring the temperature down to the point that it will not melt the turbine blades. This is great because what ends up happening is at the end product of a turbojet process, you still have a substantial amount of oxygen in the exhaust gases. However, you've not only cooled the air by dilution, but the amount of energy that's taken out by the turbine stages causes a lot of cooling, shrinking, and decrease in pressure of the gases that are coming out of the exhaust stage. So what the afterburner does is it takes advantage of that residual oxygen, adds additional fuel, and reheats those exhaust gases. It can double or triple the volume of those exhaust gases. It's often called a reheater or an afterburner, same principle. By increasing the volume of those gases, if you don't increase the diameter of the duct through which they're passing too much, the only way for that much larger volume to get out is it has to get faster. It has to accelerate. And when you accelerate the same mass of air, you increase the momentum, mass times velocity. And momentum is another name for thrust when you're talking about turbojet engines. This is great. I mean, when you think about it, it's lightweight, it's easy to build, there are no moving parts, and because you can fabricate these such that there are no metal contacts to the flame, you can go to extremely high temperatures in the afterburner. So you might think then, why aren't afterburners put on all jet engines? The problem is very low fuel economy. You can double the fuel flow in an afterburner, double the fuel flow that you're normally using in the basic turbojet engine, and increase the thrust maybe 60 or 70%. And that might be acceptable if you're trying to take off from a carrier deck or you're in a combat maneuver. But if you're flying a commercial jet across the Pacific, you're going to probably end up in the water. Now, the reason for that is not because the afterburner fails to burn all of the fuel. It does. It's an efficient way to burn the fuel. The reason for this is a fundamental physical property that is inescapable, and it's present in the operation of any kind of internal combustion engine, and a jet engine is an internal combustion engine. This principle is so important that even though I reviewed this some time ago, I'm going to go through it again because I think it'll help to understand what I'm talking about. If I take this air piston here, and I plug the output hole from this, and I compress the gas inside of the cylinder, my muscles are doing work on the gas inside the cylinder, force times distance. If I allow the piston to move back, the gas to expand, the gas does work on my muscles. 1 unit of work in, 1 unit of work out, no big deal. If, however, I take this piston and I compress the gas to twice the original pressure, then I place it in a heat source and begin heating the gas to twice its absolute temperature. So if it's 300 Kelvin, it goes to 600 Kelvin. If it's 0 degrees Celsius, it goes to 300 degrees Celsius. At that point, the pressure of the gas molecules inside roughly doubles. Now when I allow it to expand, the force at every point in that expansion is twice as great as it was when I compressed it. So I get 2 units of work out. 1 unit in, heated up, 2 units out, 1 net unit of work. Okay, do it again. But this time I push the cylinder in much harder and I bring the pressure to 4 times its original level. Now, again, I heat the gas. Same amount of heat, same number of air molecules, and I bring the pressure up to roughly twice its original point. Now when I allow the piston to move back, it's moving farther and at greater force, and so I get 2 large units of work in. The point being that the more work you invest in the beginning, in the compression stage, the more usable work you can get out at the end. Now, for you physicists out there, yes, I am rounding off some of the ideal gas law numbers, but the underlying principle remains. More compressive work in, more usable work out. And this is one of the reasons why a diesel engine is more efficient than a gasoline engine. A typical gasoline engine will have a compression ratio of maybe 8, 9, 10 to 1. A diesel engine, maybe 18 to 20 to 1. And a high-performance turbojet engine can exceed 50 to 1, 50 to 1. It's a very efficient heat engine. And that's what the problem is with the efficiency of an afterburner. Because the turbine stage has removed a lot of work energy from the fuel, from the gas, the pressure drops inside of the afterburner. And so when you're adding the fuel, you're adding it at a lower compression ratio than when it was burnt inside of the turbojet. There's no way to avoid that. But if you want to take off from a carrier jet deck, it's the way to go. And if we really don't care about fuel prices, you know, they're as low as they're ever going to get right now, then we don't care either. We just want more power. So with that basis in physics behind us, let's go outside and let's fire up the turbojet engine. All right, this is the turbojet, and as you can see, it looks pretty complicated. You can put down your paper and your pencil. If you're interested in designing something like this or using some of the ideas that we have, we're going to follow this video with a series of short, few-minute videos that are going to break this down into all the subsystems, including the source for the parts that we're using and how we build this and how we operate this. So for today, you can just watch me go through the abbreviated startup sequence and enjoy. So let's get going. All right, let's get some headphones. Now we're going to start by turning on the oil pump and the fuel pump. We're going to adjust the oil pressure to about 40 psi. And the fuel pressure to about 50 psi. Now when I turn on the starter fan, everything is going to get so loud, everything will have to be in text boxes. You're not going to hear me. All right, here we go. Turning on the fuel. All right, one of the nice things about having the starter fan on here is that when we're done with a run, rather than waiting an hour for this thing to cool off as it radiates its heat, we can run this at a low level for about 10 minutes and we can exchange parts. So I'm going to do that right now. Okay, so now let's get into the nitty and the gritty of the actual afterburner design. Now, this is a nozzle. I took this off the jet engine that we just demonstrated. And almost invariably, you're going to want to have a nozzle on the output of any kind of a turbojet engine. The reason for that is that the exhaust gases that come out behind the turbine, or in the case of a turbocharger, from the exducer, are still under some residual pressure, and you want to convert that pressure into greater velocity. What the nozzle does is just like putting your thumb over the end of a garden hose, it causes the gas molecules to speed up. More momentum, more thrust. Now, the design of a nozzle is, in theory, pretty difficult to model because there are so many variables. It depends on the AR ratio of the turbocharger. This is a value that determines the mass flow versus compression ratio of a particular model, and it varies. It also depends on what kind of pressures you're running inside of your combustion chamber, even the bypass ratio and the fuel that you're using. It's pretty difficult to model. But in practice, it's actually very easy to do. What you do is you obtain a flange that will mount onto your turbocharger and then place a rather aggressive taper on the output. Aggressive being that if you start with a ratio of 2 to 1 in area, so not diameter, but the area of the output is half the area of the input, this is almost certainly going to be a little too much. Once you've fabricated that, bring it out to the engine, connect it up, and run it up. Measure your fuel flow, your pressure, your thrust, your temperatures. Then take it off, bring it inside, and slice a couple of millimeters off, opening up the aperture just a little bit, and test it again. Do this several times until the numbers that you care about stop getting better. You're done. It's that easy. And it might sound like a little bit of work, but it's fun because that's why you built the turbocharger in the first place into a jet engine. You want to mess around with it. Now, the afterburners themselves are relatively easy to build because of the fact that there's so much aftermarket availability of compatible components to turbochargers. You can get flanges of different sizes and styles, T3, T4, 4-bolt, flares, tapers, tubing, that all sort of work together. So that all you really have to do is cut the tubing, drill some holes, and do some welding. It makes it a lot easier for you to do simply because you don't have to fabricate the tubes. Now, the designers of a military afterburner face much bigger challenges because if you're going to put an afterburner on a fighter jet, you want it as light, as compact, and as efficient as possible. You don't want a huge stovepipe sticking out of the back of a fighter jet. The problem is that turbojet exhaust velocities, even in our little turbojets, approach Mach 1. And so literally you only have a few milliseconds for all of the fuel to be added, mix and blend, evaporate, burn, and expand before it gets out of the exhaust duct. That's tough. And it has to happen inside of the afterburner. If you have the burn continue outside of the afterburner, it may look cool, it may look like a nice blowtorch, but it does nothing because all of the expansion of the gas is happening in the free atmosphere. It has to happen in the confines of the duct in order for that velocity to accelerate and produce more thrust. So what the professionals do is they install what are called turbulators or flame holders. These are little obstructions that are placed in the output of the exhaust of the jet engine. Often they're shaped like V grooves in rings or in bars across the output. And they do two things. One is they increase the turbulence and the mixing of the fuel and the air. That's important. But more important, what they do is they produce a shadowed area of relatively low velocity gas right behind them. That's important because it's very difficult, if not impossible, to maintain a stable flame in an exhaust velocity that exceeds the flame front propagation velocity. It's one of the reasons why you could put out an oil well fire with a stick of dynamite. So by placing these things in the exhaust, you improve the stability of the flame. But anything that you put in the exhaust path obstructs some of the exhaust coming out of the engine, so can decrease the efficiency of the underlying jet. So it's a very delicate balance that they have to perform to get good performance overall. We're not putting these afterburners on a fighter jet, and so we can take advantage of a few tricks that makes this a lot easier to do. First of all, we can make the ducting that the afterburner much larger in moving through it more slowly. Then we can make it much longer so that more slowly moving gas has to travel a longer distance. This gives us more time for the reaction to occur. In addition, the flare, or the increase in diameter of the tubing, also introduces turbulent mixing. Gas that's traveling right up the axis, the center portion of the output from the jet engine, is moving fastest. The gas that's sliding along the walls is moving more slowly, and so what you get is sort of a rotating toroid or donut or smoke ring as the gases are moving up the end of the tube. This can be enough to give you a stable afterburner function. We found it was a little iffy, so we decided to add some flame holders, and I found kind of a neat and convenient way to do this, and it's very flexible. Right at the point where the tube has increased in diameter and the gas velocity is decreased, drilled 8 holes, 4 pairs, 180 degrees apart, and then welded on some threaded studs over those holes. Then you take a solid rod, like this piece of tungsten welding rod, and you cut it to slightly longer than the outside diameter of the tube. Insert it into opposing holes, and then just take some screws or some set screws and lock it into position. What's nice about that is you can add 1, 2, 3, up to 4 flame holders of varying diameters. An even better way that we did in sort of version 2.0 is we took some thin wall stainless steel tubing, cut it to slightly less than the inside diameter of the tube, located it over the holes, and then drove screws into each end that allows us to lock this into position. This also gives us the ability to add a wide variety of different diameter tubes, and another little trick is in the middle position, put this in a vise with a couple of metal blocks and squish the middle together so that when these stack, they can stack more closely together, and you make the segment where the flame holder is a little bit thinner. Just makes it more convenient. And it works. I know a fair amount of engineering, as I'm sure a lot of you do too. And there's always a risk that you can get a little cocky. You can think you know a little bit more than you actually do. And that's particularly egregious when you ignore real-world evidence because it kind of gets between you and your beautiful design or your theory. And I'm guilty of both. The auto-ignition temperature of kerosene or jet fuel is 210 degrees Celsius, which is about 1/3 to 1/4 of the exhaust gas temperature coming out of the turbojet. So I was certain that as long as I got real good mixing of the fuel in the air, it would just burst into flame. Despite the fact that I was aware that most, if not all, military afterburners include a secondary ignition source in the afterburner. And I had seen a video from a really good channel on turbojet engines called Agent JZ. You might want to check them out. About 10 years ago, they ran a J79 turbojet engine that had been outfitted with an afterburner. And during the test, the afterburner secondary ignition system failed to light. And they ended up blowing jet fuel into the field behind the test shed. Didn't work. But I just plowed right ahead, put the afterburner on the engine, ran everything up, and it didn't work. So I ended up drilling a couple more holes, welding on some larger studs and threading them to put a spark plug inside of the afterburner. Ran it up again with a second ignition system, worked like a champ. You live and you learn. Now I'm still not certain why it doesn't work. The best theory I have at this point is that auto-ignition temperatures are published for atmospheric oxygen levels. And although there still is a substantial amount of oxygen in the gas coming through the afterburner, the turbojet has consumed a substantial amount as well. So it may be that the auto-ignition temperatures are much more sensitive to oxygen concentration than I had thought. Now, if you know the answer or you have a different theory, put it in the comments section below. I read them all, and maybe you come up with a better answer, and I'd be really interested in hearing about it. Now, this is generally where the amateurs stop. It's not where the pros stop, and not where we decided to stop. If you're going to bother to invest in putting an afterburner on a jet engine, you want the most punch out of that afterburner you can get. In other words, you want the flame temperatures in there as high as possible. However, nearly 3,000 degrees will melt just about anything you could make the duct out of. So what they do cleverly is they build a second inner shell or cylinder of thin steel and perforate it with thousands of tiny little holes. That cylinder sits inside of the duct with a little annular space between the duct wall and the cylinder. And some of the exhaust gases that come from the turbojet actually travel around in between that gap and bleed in through those holes, providing a little inner buffer layer between the hot flame and the steel. It works. If you take a look at a typical example of an afterburner firing up on a fighter jet, you'll see that the gases inside are incandescently hot. But the walls, if they're glowing at all, are usually glowing a relatively dull color, or they're not even glowing. It does work. So that's what we did in version 2.0. Fabricated a container tube, or an outer tube, out of thin wall stainless steel tubing. Welded a flange on the back so that we could mount this on the output from the jet engine. And then placed a feed through for the spark plug and for the fuel. This tube here is about 3.5 inches OD, or about 8.5 centimeters, and it's about 1/2 meter long. At the far end, we put a small reduction in diameter, a little nozzle. But you'll notice that this nozzle is substantially smaller than the one that was used on the same engine, because we need to get out a much larger volume of gas that's been created by the additional heat. Inside of this tube is the inner liner tube. What I did with this is took a shorter piece of stainless steel tubing. This is about 40 centimeters or 16 inches long. Placed it on a lathe and just used the lathe to scribe lines about 1 centimeter apart, and then drew lines with the tool, 16 lines like this, to produce a grid to locate the position of the holes. Then welded a cone on this end and threaded the end of the cone to accept a 1/4 NPT fitting, sort of a plumbing type fitting. And I have a right angle yaw lock fitting right in here that screws in. And in the end of this fitting, I placed a misting fuel nozzle like this. Now, because I didn't want to reach in order to be able to get this inside, I simply took the inside of the tubing of the right angle fitting and threaded it for 1/8 NPT, a much finer thread like this. Put this thing in the lathe and turned down the outer mushroom shape of the end of the nozzle. This is the exact same nozzle turned down and before fabricating, so that this entire apparatus can slip in from the end and I can change different nozzle sizes. This produces about an 80-degree spread of fuel into the cone and into the beginning part of the tube here. Then welded 4 studs on each end, 90 degrees apart, that keep this centered inside of here, and then began drilling holes. The design of the holes is similar and based on the same philosophy of the flame holder inside of a turbojet engine. We start out with a large number of very tiny holes that provide mixing of the fuel and the air and a relatively low air velocity. Then we complement that by threading some of those holes and placing some fine thread button cap head screws. This provides the flame holders. And then right behind that mixture of fuel and air, we locate the port for the spark plug. That fuel that begins burning here is still burning pretty rich, and as this moves down, it begins to gain more and more air to assure that we get a full burn of the fuel-air mixture. Finally, near the end, I increased the number of holes to make sure that we didn't get any flow resistance from the large quantity of air that's coming into, or gas, exhaust, coming into the afterburner engine. An interesting thing you can see, something that I didn't optimize, is the color differential here. I probably should have started these holes a little bit lower, maybe a little smaller, maybe not so many of them, because as the gas was flowing into the tube and the pressure was dropping on the outer annular space between these two tubes, we were getting less and less protective cooling at this end, and this end got a little bit hotter. It didn't melt it, it certainly didn't make it not function, but you can see it's somewhat of an iterative trial and error type of process. 240 holes here, 120 holes here, 60 holes here, 3 millimeters, 5 millimeters. That's it. Now the way this assembles is Let's see if I can get this lined up. The inner tube feeds into this outer tube with minimal clearances, so I have to sometimes wiggle this around a little bit to get it to fit. There we go, piece of cake. Then as I slide this in, when this hole lines up with the spark plug, this input for the yaw lock fitting lines up with the input of the fuel. We get this in here like this. Get the pipe to seat in here, tighten these nuts like this, install the spark plug like this, and we're ready to go. So let's go outside, hook this guy up, and I'll show you how it works. All right, so we've installed this on the end of the turbojet. We're using a little flare coupling to allow us to use a V-band clamp that takes the two flanges and holds them together. And by tightly screwing this together, it squeezes this and puts a lot of pressure on the two approximating faces. This is the fuel supply for the kerosene, or the jet fuel, that goes into the Afterburner. This is a check valve that prevents retrograde flow. If we had any kind of a problem, we're not going to feed hot gases into the fuel system. This is the spark plug, and this is a secondary support system that just provides additional support so that we're not just levering everything off of the end of the turbojet. So now we're ready to go. Let's get this thing fired up. All right, so now what we're going to do is run it up the same as we did the last time, except now I have the separate fuel pump and the ignition system for the Afterburner. So here we go. Turn on the oil pump and adjust it to about 40 psi. The fuel pump, adjust it to about 50 psi. All right. Then we hit the ignition and turn on the fan. It's going to get pretty loud. It works. Now, the interesting thing about an Afterburner is that you can put almost anything you want through there to burn. You can use jet fuel or kerosene. You can use diesel fuel. You can use alcohol, isopropyl alcohol, and even rum. Disappointing thing is it's so hot, once you fire it up, you can't smell the rum, but it does work. In addition, you can use the same design to put other things through the Afterburner that you don't burn. So what we're going to do is we're going to refit this with model 1.0, and we're going to put some fog juice through it. We'll see what happens. Okay, so we took out the Mark II Afterburner and put in Mark I. This one does not have any ignition system hooked up to it, and we took off the accelerating cone on the end but left the flame holders. And this is what we're going to be pumping the fog juice into. I think you'll like it. All right, so we're going to run it up one more time. We're going to use the Afterburner fuel system, not the ignition system, to pump in the fog juice. Here we go. Gonna be loud. Man, I love my job. This is a heck of a lot of fun. So in any case, you can use these afterburners for a variety of different purposes. And if you want to produce fog and you don't want to just do, say, a high school performance of Riverdance or a little disco performance, but you want to, say, cover the intersection of a road or maybe a small town, this is your baby. We're also going to be following this up, as I said, with several very short videos that break down the subsystems of this unit so that you can reproduce this, and we'll give you all the parts and pieces and plans and ideas about what you need to know in order to be able to make this work. And I want to thank you very much for watching. Stay safe, you have a lot of fun, and we'll see you soon.